Here we go. All right. So let's keep going. Here we go. Here we go. Here we go. Now this one's a little bit different. Notice our divisor here is x plus 5, right? Okay. You can still use synthetic division. Your divisor's always got to be x minus something. Okay? That's how it's set up. So when you have x plus 5, you can really think of this as x minus negative 5. X minus negative 5. So the negative 5 is what's going to go here. And then just like before with capital F of x, right? We have our again, the coefficients. Each one gets its own column. So we have 1x cubed, so that's a 1. 9x squared, we have 9. 23x is 23. 15 is 15. And now we just do the process, right? So this one's going to come down, as you can see. Now what's going to happen next is negative 5 times 1 is negative 5. Negative 5 times 1 is negative 5. That's going to go here, which is shown on the next slide, right? And what do? You add and you get 4. That's what's happening. Next is negative 5 times 4. That's negative 20, right? That's going to go here. Negative 20. Okay, that's good. What's 20 now? Negative 20, then you add, right? And you're going to get, excuse me, you're going to get 3 down here. So again, let me say it again. Negative 5 times 4, that's negative 20. Okay, that's what goes here. Then we add to get 3. Okay. Okay, that's good. Then finally, we have negative 5 times 3. That's negative 15, which goes here. Okay. And then you add, you get 0. Nothing after that, so we stop. Okay, so we have all this. What does this tell us? Well, for one, it tells us that the quotient is going to be, again, 1 degree less. So it's x squared plus 4x plus 3. And notice here, our remainder is 0. So we really have, from the division algorithm, we have this. Quotient, remainder, we can write it this way. Again, the remainder is 0, so we have this. Okay, so this is our remainder. And here all I did was I replaced it with x plus 5 because, again, you had x minus negative 5 here, okay? But there's something else you should notice. Notice if the dividend was this, right? The x cubed stuff, you know, capital F of x. If you evaluate that at negative 5, okay, you actually do get 0, which is what the remainder also is. Okay, so you do actually get 0, which is, in fact, what the remainder is. Okay. So here we get we got this to be 0. The remainder is 0 as well. And again, what are we doing down here? We're evaluating our dividend at negative 5. Well, this is not a coincidence. There's actually a really nice theorem called the remainder theorem. And it's really proven by the division algorithm. Namely, if you have a polynomial capital F of x, right? And if you divided it by x minus a, you can get the remainder easily by not even dividing. It turns out the remainder is this constant, f at a. And again, it's really just from the division algorithm, because if you're dividing by x minus a, you can find a polynomial q, capital Q of x, which is our quotient, and you do find a remainder R of x, such that this is true, but then you can replace x by a to get the remainder has to be this. So that's what we get here. Okay, that's great. As another example, let's suppose we wanted to divide this here by x minus 3. We could actually get our remainder immediately. I mean, we did this already. We got the remainder to be negative 4. I think it was the first example we did. Yeah, it was the first example, right? And we got the remainder to be negative 4. But again, if I evaluate this at 3, right, it's x minus a, it has to be minus here. So at 3, we evaluate it, we get negative 4, which is our remainder. So that is, in fact, a remainder theorem, which is very, very nice. Okay, I'm not done yet. Don't worry, I have other slides here we can use. Okay. All right, let me get to the other notes. Are there any questions about this, though? Actually, you know what? Let me do this. I could slow down a bit. I don't want to go too fast. Oh, yes.
So we can use any one we want to like do the division, like any way of doing it.
Yeah, if you have x minus, if you're dividing by x minus a number, you can use synthetic division. If you don't have that, though, then you have to use long division.
Okay, thank you.
Okay. You're welcome. Good question. Okay. Any other questions? All right, let me stop sharing this and get to the next set of notes. But again, if I go too fast, please tell me. I don't want to go too fast, because if I do, then no one benefits. So, all right, let me share these notes. Okay, I'll send these notes out as well after class, that is. Any second now. Here it is. So again, I'm just stating the remainder theorem. Okay, I didn't think I would get this far, so that's why the remainder theorem is stated twice. Okay. That's not device 7. No, I need to close. Oh no, close the wrong one. Hold on. Close that. Have to reload the session. 1 second. Sorry about that. It was just internet trouble. Let me just try again. Okay. Here we go. Here we go. Okay, now I'm happy. There we go. Okay, now now the right notes are being shared. Sorry about that. Okay, I had to reload the session. It was giving me internet trouble. So, all right. So again, this is the remainder theorem. Okay. So now, okay, I just restated it. Okay, so this was the same slide we left. That was on the other set of notes. Here is basically what I said in words, why the remainder theorem is true. Again, it's just the division algorithm. That's what it boils down to. Namely, okay, if you were to divide by x minus a, where a is a constant, okay? In other words, your divisor, capital D of x, right, is x minus a, okay? Well, then by the division algorithm, what you can do is you get two unique polynomials here, Q and R, so that this is true. Okay, so that's what you get, right? You have two polynomials, Q and R, so that you can write f of x that way. And what's going to